First of all, we will define probability. The probability of occurrence of an event is defined as the ratio of the number of favorable cases in which the event occurs to the total number of cases. So, this is the definition of probability. Probability of occurrence of an event. It is equal to this ratio. Number of favorable cases in which the event occurs divided by total number of cases. For example, if we want to find the probability in this case, this is the example. By following one card out of 52 playing cards, find the probability of the card to be king. Out of 52 playing cards, there are 4 kings. So, required probability is equal to number of favorable cases in which the event occurs divided by total number of cases. It is 4 upon 52. Out of 52 playing cards, there are 4 kings. So, probability of the card to be king is 4 upon 52, that is 1 upon 13. Now we consider the distribution of 3 distinguishable particles in 2 similar boxes. There are 3 distinguishable particles and we want to distribute these particles in 2 similar boxes. Distinguishable particles are those which can be distinguished from each other. We write them by A, B, C, etc. And indistinguishable particles are those which cannot be distinguished from each other. We write indistinguishable particles by dot. Now, if we have to distribute 3 distinguishable particles A, B and C in 2 similar boxes, in this case there are 4 macrostates. There are 4 ways in which we can distribute these 3 distinguishable particles in 2 similar boxes. These 4 ways are known as 4 macrostates. These are 0, 3. In first box, number of particles is 0. In second box, number of particles is 3. Other macrostates are 1, 2, 2, 1 and 3, 0. Zero, 3 means number of particles in first box is 0 and number of particles in second box is 3. And now we increase this number of particles in first box. After 0, we write 1, 2 and 3. And number of particles in second box are reduced 3, 2, 1 and 0. So if we want to distribute 3 distinguishable particles in 2 boxes, there are 4 macrostates 0, 3, 1, 2, 2, 1 and 3, 0. These 4 macrostates are shown in this table. There are these 4 macrostates 0, 3, 1, 2, 2, 1, 3, 0. And in next column we write microstates. In macrostate we write only the number of particles in each box. And in microstates we describe which particles are in first box and which particles are in second box. So corresponding to the macrostate 03, only one microstate is possible. First box is empty and all these 3 particles A, B, C are in second box. But for macrostate 1, 2, there are 3 microstates. 1, 2 means number of particles in box 1 is 1 and number of particles in box 2 is 2. Now we have these 3 ways by which we can distribute these 3 particles, such as in first box we have 1 particle and in second box we have 2 particles. These 3 microstates are A and BC, B and CA, C and AB. Similarly, for macrostate 2, 1 we also have 3 microstates. In first box if we have B and C, then in second box we have A. If in first box we have C and A, then in second box we have B. And if in first box we have A and B, in second box we have C. And in the macrostate 3, 0, we have only one microstate. All the particles A, B, C are in first box and second box is empty. So these are the 2 columns. First column shows macrostates, 4 macrostates when 3 particles are distributed in 2 similar boxes. And corresponding to these 4 macrostates, we write their corresponding microstates. Number of microstates corresponding to macrostate 03 is 1. Number of microstates corresponding to macrostate 1, 2 is 3, and so on. These number of microstates corresponding to a given macrostate, we write it as omega I. Number of microstates corresponding to a given macrostate, this is written as omega I. So in this third column we write omega I, number of microstates corresponding to given macrostate. And for these 4 macrostates we have number of microstates as 1, 3, 3, 1. And in next column we write total number of microstates, that is summation omega I, and it is 1 plus 3 plus 3 plus 1 and it is equal to 8. Last column shows the probability of a macrostate. and probability of a macrostate Pi is equal to omega I upon summation omega I. It is equal to the number of microstates divided by total number of microstates. So for first macrostate 03, the probability Pi is 1 upon 8. For second macrostate 1, 2 and third macrostate 2, 1, we have probability 3 by 8 for both macrostates. And at last in the macrostate 3, 0, we have probability equal to 1 upon 8. So the probability is proportional to omega I. It is proportional to the number of microstates corresponding to a given macrostate. If we have more number of microstates, then we have larger probability. It is clear that total number of microstates is equal to number of boxes to the power number of particles. Correct this. Total number of microstates will be equal to number of boxes to the power number of particles. So we have 2 to the power 3. 2 is the number of boxes and 3 is the number of particles. So total number of microstates is given by number of boxes to the power number of particles. It is 2 to the power 3, which is equal to 8. Here we have 8 total number of microstates summation omega I. It is given by 2 to the power 3. If we want to distribute 4 particles in 2 boxes, then total number of microstates will be 2 to the power 4. And number of microstates corresponding to macrostate 03 will be given by 3C0. 3 is total number of particles and 0 is the number of particles in first box. So for macrostate 03, number of microstates will be given by this formula 3C0. 3 total number of particles, 0 number of particles in first box, and 3C0 can be calculated from this formula. This is the formula NCR. It is factorial n upon factorial r into factorial n minus r. So by using this formula of NCR equal to factorial n upon factorial r into factorial n minus r, we can find this value of 3C0. It is the number of microstates corresponding to macrostate 03. 3C0 will be equal to factorial 3 upon factorial 0 into factorial 3 minus 0, and it is equal to 1. Similarly, the number of microstates corresponding to macrostate 1, 2 will be given by 3C1 and it will be equal to 3. Number of microstates corresponding to microstate 2 1 will be given by 3C2 and it will also be equal to 3, and number of microstates corresponding to microstate 30 will be 3C3 and it will be equal to 1. So these are the number of microstates which can be calculated from this formula: 3C0, 3C1, 3C2, 3C3. Probability of macrostate, we write it by Pi. It is the number of microstates corresponding to the macrostate, which we write by omega I, divide by total number of microstates, which we write by summation omega I. So probability of a given macrostate Pi will be equal to omega I upon summation omega I. Omega I is the number of microstates corresponding to that macrostate, and divided by summation omega I. Summation omega I is total number of microstates, and we find the probability of these 4 macrostates. Pi equal to omega I upon summation omega I. This is 1 upon 8, 3 upon 8, 3 upon 8 and 1 upon 8. Probability of each microstate is shown in table. Correct this. It is probability of each macrostate. Probability of each macrostate. Correct this. It is not microstate, it is macrostate. Probability of a given macrostate is shown in the table. It is clear that probability of each macrostate is proportional to its corresponding number of microstates. Pi is proportional to omega I. Probability is proportional to corresponding number of microstates. Most probable microstate is one for which probability is maximum. Correct here also. Most probable macrostate. It is not most probable microstate. It is most probable macrostate. Most probable macrostate is one for which probability is maximum. In this case, 1 2 and 2 1 are most probable macrostates, and corresponding probability is 3 upon 8. Similarly, least probable macrostate is one for which probability is minimum. So least probable state is one for which number of corresponding microstates are least. In this case, 0 3 and 3 0 are least probable macrostates, and corresponding probability is 1 upon 8. So out of these 4 macrostates, maximum probability is for macrostates 1 2 and 2 1. So these are most probable macrostates. Probability of these 2 macrostates is maximum. It is 3 by 8. And least probable macrostates are these 2, which are 0 3 and 3 0. And probability of these 2 macrostates is 1 by 8 and 1 by 8. So most probable macrostates will be those for which number of particles in 2 boxes are same or almost same. Here number of particles is 3. So number of particles in 2 boxes cannot be same. If we have number of particles 4 and we have to distribute 4 particles in 2 boxes, then most probable state will be 2 2 when number of particles in each box is same. But if number of particles is odd, then most probable state is 1 for which number of particles are almost same. Here 1 2 and 2 1. And least probable macrostate is 1 for which probability is minimum. It is 1 for which in one box we have 0 particle, 0 3 or 3 0. All the particles are in one box, either first box or second box, and other box is empty. Then this is the least probable state. Now we distribute n distinguishable particles in 2 similar boxes. Till now we have distributed 3 particles A, B, C in 2 similar boxes. Now if we have n distinguishable particles and we want to distribute these n distinguishable particles in 2 similar boxes, then number of macrostates will be n plus 1. These macrostates are 0 3. This is the first macrostate. In first box we have 0 particles. In second box we have all these n particles. And other macrostates are obtained when we increase the number of particles in first box by 1 and decrease the number of particles in second box by 1. So these macrostates are 0 n. Next macrostate is 1 n minus 1, then 2 n minus 2, and in general we have a macrostate r n minus r. If we have r particles in first box, then number of particles in second box will be n minus r because total number of particles are n. And in the last we have n0. Now number of microstates corresponding to macrostate r n minus r. If we consider this macrostate r n minus r, in first box we have r particles, in second box we have n minus r particles. Then number of microstates corresponding to this macrostate is given by NCR. We write it by omega I. Omega I is the number of microstates corresponding to this macrostate r n minus r. And this is given by NCR. N is total number of particles and R is the number of particles in first box. Number of particles in first box is R. So number of microstates will be given by NCR. So omega I is NCR and it is equal to factorial n upon factorial r into factorial n minus r. So if we want to find the number of microstates for macrostate r n minus r, it is given by factorial n divided by factorial r into factorial n minus r. In numerator we have factorial n, factorial of total number of particles. In denominator we have 2 factorials. First is factorial of r. It is the factorial of number of particles in first box, and second factorial is factorial n minus r. It is the factorial of number of particles in second box. Total number of microstates will be summation omega I, and omega I is NCR, and summation NCR will be equal to 2 to the power n. If total number of microstates is 2 to the power n, then probability of each microstate will be 1 upon 2 to the power n, and probability of microstate r n minus r will be written as p r n minus r, and it is equal to omega I upon summation omega I. It is the ratio of number of microstates corresponding to macrostate r n minus r, which we write by omega I, and divide by total number of microstates, which is summation omega I. So it is equal to NCR divided by 2 to the power n. It is 1 upon 2 to the power n, and NCR is factorial n upon factorial r into factorial n minus r. Most probable microstate, it is not microstate, most probable macrostate, correct this. Most probable macrostate is one for which probability is maximum. Most probable macrostate is one for which probability is maximum, or it is not FOUR, it is FOR. It is not of for, it is or FOR for, or for which number of corresponding microstates is maximum, or for which value of NCR is maximum. Value of NCR is maximum for R equal to n by 2. If R is n by 2, then we have macrostate n by 2, n by 2. Particles are equally divided into two boxes. Then number of microstates will be maximum, NCR will be maximum when R is n by 2. So most probable macrostate, it is not microstate, most probable macrostate is n by 2, n by 2. In first box we have half particles n by 2, and in second box we have half particles n by 2. This macrostate is most probable state. Probability of this macrostate is maximum, and its probability is given by NC n by 2 divided by 2 to the power n. So it is 1 upon 2 to the power n, and NC n by 2 is given by factorial n upon factorial n by 2 into factorial n minus n by 2. So it is 1 upon 2 to the power n factorial n divided by factorial n by 2 into factorial n by 2. If n is an odd number, then most probable macrostates will be n minus 1 by 2, n plus 1 by 2, and n plus 1 by 2, n minus 1 by 2. N by 2, n by 2 is most probable state when n is even. We can divide equally in two boxes. And when n is odd, we cannot divide equally in two boxes. Then most probable state will be n plus 1 by 2, n minus 1 by 2, or n minus 1 by 2, n plus 1 by 2. Least probable macrostate is one for which probability is minimum, or for which number of corresponding microstates is minimum, or for which, correct here also, it is not of which, it is or for which value of NCR is minimum. And value of NCR will be minimum for R equal to 0 or R equal to N. So least probable macrostates are 0N and N0 when all the boxes are in one box and other box is empty. Then this is the least probable state, 0N and N0, and then probability is NC0 divided by 2 to the power n. It is 1 upon 2 to the power n into factorial n upon factorial 0 into factorial n minus 0. Factorial n is cancelled out in numerator and denominator, and it is equal to 1 upon 2 to the power n.